Hi everyone, I hope you're doing well. In this video, we're going to take everything we've learned about activators and deactivators and go over some practice problems. All right, so let's start with an example where we have a benzene ring with two substituents attached. All right. So let's say we added a methyl group and a nitro group to our benzene ring, and the nitro group is in the para position. So how would we name this molecule? So remember, we want to try to find the parent name, and that would be toluene. And toluene is a benzene ring with a methyl group attached. But then we want to indicate where the nitro group is. So there's a couple different ways we could do that. We could say that it's in the para position, so we could just write P-nitro in front of toluene. Or we could number the substituents and say that the nitro group is at the fourth carbon in the ring. And then it's just understood that the methyl group is at position 1 since we're using that parent name of toluene. Okay, so now let's say we want to add a third group onto this ring. And let's say we want to add bromine to the ring. Which reagents would we use to add bromine to the ring? So we would use Br2, but remember, because we're adding this to a benzene ring, and a benzene ring is aromatic, we have to use a catalyst. So we would use something like iron tribromide, or you could also use aluminum tribromide. Either one works. All right, so now we have to figure out where is that bromine going to end up. We have a few different options. It could end up ortho to the methyl group or ortho to the nitro group, right? So the first thing we want to do is figure out, are the groups that are already attached ortho para directors or meta directors? Okay, so let's highlight the methyl group. We'll highlight it in blue. And let's figure out if that's an ortho para director or a meta director. So is the methyl group an activator or a deactivator? It's an activator. Or you could also say it's an electron donating group. And are activators ortho para directing or meta directing? Ortho para. Well, looking at our structure up above, the para position is already blocked by the nitro group. So bromine can't add to the para position. It would have to add to the ortho positions. Now, even though CH3 is ortho para directing, what about the nitro group? Let's highlight that in red. So is NO2 an activator or a deactivator? A deactivator. Or an electron withdrawing group. And are deactivators ortho-para-directing or meta-directing? Meta-directing. All right. So if we look at the nitro group, where are the meta positions relative to the nitro group? So they're going to be 2 carbons away, and it looks like those are the exact same positions as our ortho-para positions relative to the methyl group. Okay, so that means bromine is going to add to one of those positions, and it ends up being the same molecule no matter which side you add it to. All right, so our final product looks like that. So we've got our methyl and nitro groups opposite each other, and then bromine is right next to the methyl group in the ortho position, but it's also meta to the nitro group. So it all works out. Okay, so let's talk about some strategies for solving this type of problem. So how to choose the best substitution position, I guess we could say. So 1, identify the substituents as ortho-para directors or meta directors. And then 2, if a tie occurs, then the strongest activator wins. So for instance, let's say you had 2 ortho-para directors, and you might have different positions that the substituent could end up in. You're just going to go off of the stronger activator. So remember in that chart that we saw in the last lecture, everything was ranked from strongest activator to strongest deactivator. So you can just go off of that chart. All right, and then third, if you're still tied, just pick the most accessible position. So we'll talk a little bit more about what that means later. But it has to do a little bit with sterics. Oops. Almost wrote sterics instead of tied. Ah. Okay, so let's look at another example. So this time, let's say we have 3 groups on our benzene ring. So we have a methyl group, and then next to that is an alcohol. And then across from the alcohol is a nitro group. And let's say we want to add bromine to the ring. Try to figure out, using the rules that we saw on the last slide, try to figure out the product. So you can pause the video and try this on your own first, and then when you unpause, we'll go over it together. All right, so let's start with identifying whether each substituent is ortho-para directing or meta directing. All right, so we'll highlight the methyl group in blue. So we already said previously that CH3 is an activator, which means that it is ortho-para directing. Okay, so looking at our ring, one of the ortho positions relative to the methyl group is taken up by the alcohol. But the other ortho position is free, and the para position is free. Okay, so those are some possibilities. Let's look at the alcohol. So is an alcohol group an activator or a deactivator? An activator. So it's also ortho-para directing. Okay, so let's look at the ortho positions relative to the alcohol. One of the ortho positions is already blocked by the methyl group, but the other ortho position is free. And then it looks like the para position relative to the alcohol is blocked by the nitro group. So there's really only one spot that the bromine could go if the alcohol is our main contributor here. All right, and last but not least, let's look at the nitro group. And previously we said that NO2 is a deactivator. And we said that that means it's a meta-directing group. Okay, so let's look at the meta positions for NO2. Let's see, one of the meta positions is blocked by the methyl group, but the other meta position relative to NO2 is free, and that lines up with the alcohol ortho position. Okay, so how do we decide where bromine goes? Because it looks like there's a bit of a tie in terms of where things could end up. So let's go to rule number 2. If a tie occurs, then the strongest activator wins. All right, so which activator is stronger, the methyl group or the alcohol group? The alcohol group. So that means bromine is going to add to the ortho position relative to the alcohol, and then that's also the meta position relative to the nitro group. Okay, so let's draw our final product. So we still have our methyl group, our alcohol group, our nitro group, and bromine is going to add to the ortho position next to the alcohol. All right, so that's our product. Okay, so now let's talk a little bit about steric effects. So sometimes we can come across a situation where something could add ortho or para, so you end up with a mix of products. But which product would be the major product and which one would be the minor product? So as an example, let's look at toluene. Okay, and let's say we're adding bromine again. We already said that the methyl group is an ortho-para director. So our bromine could end up in either the ortho or the para positions. So let's draw those two products. And for the ortho product, you could draw the bromine on either side of the methyl group. It's still the same product because you can just flip it like a pancake. Okay, so Let's see. What would be the major product here? So, which position is present in a larger amount, ortho or para? Ortho. So the ortho product will be the major product here, and the minor product is the para product. Okay, what if our methyl group is actually a tert-butyl group, so it's quite large and takes up way more space? So I'll try to draw it big so it looks as large as it should be. And let's try to add bromine again. Okay, so is that tert-butyl group an activator or a deactivator? So remember, really any alkyl group is going to be an activator through hyperconjugation. So that means it's also an ortho-para director. Okay, now what we saw up above was that the ortho position would be the major product and the para position would give us the minor product. However, in this scenario, tert-butyl is quite large, so there's going to be some steric effects going on here. So let's draw our two possible products. And which one do you think will be the major product and which one will be the minor product? So in this scenario, the major and minor products are actually flipped due to sterics. So the ortho product is the minor product. And that's just because it's going to be really difficult for a bromine atom, which is quite large, to kind of tuck itself in next to the tert-butyl group. So if we were to kind of draw this to scale, the bromine atom is really large. But remember, each of these carbons has 3 hydrogens bonded to it, right? So there's going to be some difficulty having those two groups right next to each other. But the para position is nice and open, so that will be our major product. So let's highlight the major product in yellow. And we'll highlight the minor product in red, just so we can kind of see that they're flipped. So the main message here is that we're going to assume the ortho product is major unless the substituent is large, and then it flips. All right, now let's also talk about blocking groups. So here we can see that we end up with a mixture of products. But what if we just wanted one product? What if we just wanted to form the ortho product, for instance, and we did not want to form the para product? All right, so let's say that we have our tert-butyl group on the ring, And we want to add bromine just to the ortho position. We do not want it to add to the para position. How would we do that? So one way we can do this is by blocking the para position. Now, typically, the para position would be the favored position because we just saw that due to sterics, bromine would prefer to be in a more open area, right? Kind of away from the tert-butyl group. So we do want to try to block that spot since it is the favored spot and just form the ortho product. So we can add something to the para position, and it should be something bulky so that it only adds to the para position. So we're going to use sulfonation. And how do we add that sulfur group, the SO3H group, to the para position? What reagents would we use? So remember, we use fuming sulfuric acid. Now again, it's only going to add to the para position because it is so bulky, and we already have a pretty bulky group up above, so it won't add to that ortho position. All right, and then we can add our bromine. So now the only available positions are the ortho positions. And it doesn't really matter which side bromine is on because we can flip it like a pancake. And then we need to remove that sulfur group. So remember when we talked about sulfonation last week, we said that it's a reversible process and it just kind of depends on the concentration of the acid. So if you want to add that sulfur group, you use fuming sulfuric acid. If you want to remove it, you just use dilute sulfuric acid. So super easy. And then your yield for the ortho product is about 100%. So these are all really cool tools that we can use to create these different products that we want versus the products that we don't want. All right, so we'll end the video there. In the next video, we're going to talk about some synthesis strategies using everything we've learned so far. And we'll go over some tips for how to kind of get the product that you want. So I will see you then.